Namaste students, welcome back to Rama Teaches You. Today we're going to do the class IB Physics, class 11th. It's going to be chapter E1, Structure of an Atom, the third video. Okay, so in the previous two videos we had discussed how an atom actually exists in nature and what are the various characteristics that an atom has. Okay, we did the J.J. Thomson's model of an atom, the plum pudding model. We also did the Rutherford's model of an atom using that the nuclear model of an atom. And in the last class, I gave you a brief introduction on the absorption and the emission spectrum. And then we did the emission spectrum. Okay, so today we are going to start with the more detailed analysis of absorption and emission spectrum. Let's start the video. Okay, now the atom in a solid. Last we discussed about something known as a Planck's constant. Okay, I'll just give you a brief about what we discussed last time. Max Planck was a physicist who basically described the radiation not just simply as a wave, but he considered them to be particles or packets. And these packets of radiation were known as quanta. And when the radiation lies in the visible spectrum, we call it a photon. Now, Max Planck was able to create a relation between the energy that a packet of radiation holds to its frequency and wavelength. He called it E is equal to h mu, or Planck's constant multiplied by frequency, where the Planck's constant is equal to 6.626 or simply 6.63 into 10 to the power minus 34 joules second. Okay, so basically that is the Planck's constant. Now, what is the SI unit of frequency? The SI unit of frequency is per second, right? Hertz or per second. So basically, if you multiply joules second with 1 upon second, you will get joules, and energy is always measured in joules. Okay, similarly, we know the relation between speed of light, frequency and wavelength are c is equal to f lambda. Therefore f is equal to c upon lambda. Therefore you get another formula for doing the same calculation. So E is equal to mu f or h mu or hc by lambda. Okay, now the atoms in a solid, liquid and high pressure gases are also excited through the energies available at suitable temperatures. Okay, if you place these atoms and molecules of solids, liquids and high pressure gases in a suitable environment and increase their temperature or increase it to a suitable temperature, you get to make these atoms and molecules excited. But the emitted light observed under such conditions consists of a band of colors rather than lines. In solids, these bands themselves merge to give a continuous spectrum with no single color at all. This is typical of matter in which atoms are closely packed. So instead of, see, when we were trying to energize or excite an atom or a molecule of a gas at very low pressures, we used to get these types of emissions. Okay, that is discrete line emissions were observed. But if you have solids and liquids and very high pressure gases, then instead of getting discrete lines, you get a continuous spectrum of colors, right? You get a continuous spectrum of colors. Each atom is modifying the energy state in the nearby atoms. For a large group of atoms, the overall energy level combine to form a series of similarly streamed energy levels. Okay, this gives an energy band rather than a set of lines. Instead of having a few set of lines, you get an energy band. Why is it happening? It is happening because if one atom in a solid is excited, okay, if one atom in a solid is excited, then that atom may try to excite the neighboring solids also, neighboring atoms also. Okay, so instead of simply having a discrete energy level or discrete radiation come out, you get to have a band, complete band of colors in understood. So so this is the continuous spectrum. This is the emission spectrum. Okay, emission spectrum happens when you have a dark background and colorful lines observed on the dark background. Absorption spectrum is when you have a continuous spectrum and the atom absorbs certain frequencies of light or certain wavelengths of light, you get the absorption spectrum. A colorful background with dark lines in between. Okay, now in 1868, solar eclipse. Astronomers analyzed the spectrum of light from the sun during the eclipse. They discovered a bright spectral line at 587.5 nanometer, which could not be accounted for from the spectral lines of known elements. They proposed that it must be a new element and called it element helium. Okay, now basically on Earth you have helium. It's not that in Earth you don't have helium, but the thing is, helium does not react with anything. So for us humans to detect helium, we had to we had to rely on the sun. Okay, we observed a new element helium in the sun, and then we started figuring out whether we have helium in the Earth's atmosphere or not. Okay, we have helium. All the balloons that we have in the birthday parties that flow up are made up of helium. Okay, so after helio, the Greek word for sun, 14 years later, helium was discovered on Earth. Okay, and that gave rise to a new set of elements known as the noble gases, gases that do not react with anybody. Clear? Okay, now absorption spectrum forms in a similar way. A hot object, whether solid, liquid, or gas, emits a continuous spectrum. When the hot object is surrounded by a cooler gas, the radiation from the hot object must pass through the cooler gas to be observable. The original continuous spectrum is now seem to be crossed by several dark lines. Okay, so when you have a hot object, it is releasing a continuous spectrum. This continuous spectrum of lines is the continuous spectrum is going through a gas, and the gas selectively absorbs certain frequencies of light from that continuous spectrum, thus resulting in the formation of dark bands. Okay, these dark lines that you observe here, okay, these are the ones that I'm talking about. This. These are all dark bands. When a heated tungsten filament is viewed through a hydrogen gas, the absorption spectrum shown in the bottom diagram of figure 16 can be seen. So tungsten is what? Tungsten is the filament that was used in the incandescent bulbs. You remember the incandescent bulbs that we used to have at home in Kerala, in Madras and all. So those incandescent bulbs basically they used to glow bright white. A bright white color is mix of all the colors. Okay, you can get bright white color only when you have a combination of all the colors. Okay, now so the black light when tungsten is heated and you pass that colorful light through a prism and then through the gas, what do you see? You observe that some dark lines are observable on this continuous spectrum. These dark lines are the lines that are absorbed by the hydrogen atom. So the light that was coming from tungsten, when it passed through the atoms of hydrogen, through the molecules of hydrogen, what you observed was the electrons that were present in the molecule of hydrogen, they got excited. Okay, they got excited, they went to a higher energy level. Okay, and when they went to this higher energy level, they required some amount of energy, and that energy was taken in by this colored spectrum. Okay, from this colored spectrum some amount of energy was taken, and that is the black lines that you see here. Okay, this dark lines that you see here. Now, when a heated tungsten filament is viewed through a hydrogen gas, the absorption spectrum shown in the bottom diagram figure can be seen. The black lines occur at precise positions of the line of hydrogen in the emission spectrum. Now, if you were to do this experiment in Bahrain, and if I were to do the same experiment in India, and we take a photograph of the spectrum that we have, yours and mine will be the exact same, because hydrogen in Bahrain and hydrogen here is the same. Okay, every single hydrogen atom would result in the formation of the same these dark absorption spectrum bands. Okay, now the absorption occurs when an atom of a cooler gas absorbs a photon of energy identical to the difference between the two of its energy levels. This photon promotes an electron from the lower to a higher energy level state. The cooler gas therefore removes photons with this energy difference from the continuous range of energies emitted by the light source. Now, we know that hydrogen atom, around the nucleus there are certain permissible energy levels. Okay, electron, when it is present in one energy level, it won't lose any energy, but as soon as the electron is excited, okay, it will only absorb enough energy to go from a ground state to an excited state. That's it. It won't absorb any extra energy. Okay, because it does not require any extra energy. Like, for example, when you go to a restaurant, you will only eat till your stomach is full, right? You won't eat till you vomit. You will only eat till your stomach is full, and after that you will leave. Similarly, what happens, this hydrogen atom, it has electrons that will jump from a ground state to a higher excited state, and to go from this ground state to a higher excited state, they require some amount of energy, and that some amount of energy is only by the absorbed from the continuous spectrum. So that is why we have these discrete lines. Okay, understood. So this is proof that there are certain energy levels around the nucleus of an atom. It is proof. The absorption spectrum is the proof that we need to show that there are permissible energy levels around the nucleus of an atom. Now let's see further. The absorbing atom is now in a higher energy state. This makes it unstable. Okay, it reverts to its lower energy level by photon emission. This photon has the originally absorbed frequency. However, it is emitted in a random direction, not necessarily in the direction of the original photon. This reduces the intensity of those specific emission line frequencies in the original direction. An electron usually stays in its excited state for less than 10 to the power minus 8 seconds. Okay, 10 to the power minus 8 seconds is the average time interval for an electron to stay in that excited state. It will go up and then it will come down. Understood? Clear? So the black, and when it comes down, you may think, Anna, if it is coming down like this, then why is the absorption? So it will release a certain photon, right? For example, let us imagine if hydrogen absorbed a wavelength of, let's say, 520 nanometers. It absorbed a wavelength of 520 nanometers. Then when it comes down, it will release a wavelength of 520 nanometers. Okay, but it is not necessary that it releases the electron in the path of light itself. For example, I'll give you an example. Okay, now you are in front of a stadium. Okay, there are a few people in front of you throwing balls. They are throwing balls in your direction. So what do? Out of 10 balls that are thrown at you, you may be able to catch like 2 or 3 balls, right? Then you have two options. You can either throw the ball in the direction in which the people were throwing, or you can throw the ball that you caught in a random direction. Okay, so that is what's happening here. The atom, the electron that has absorbed this radiation, it is not necessary that it releases this radiation in the path of the original light. It will throw this in some other direction. thus reducing the intensity of that particular frequency in that spectrum. Okay, understood. So basically, 10 people were throwing 10 balls across you. Okay, you are here, people are here, and then these people are trying to throw a ball behind you. Okay, these people are trying to throw a ball behind you. But what do? Because you are between the path of the ball, you catch a couple of balls, you intercept them. Okay, you have two options. You can either throw the ball behind you, or you can throw the ball in a random direction. Okay, but majority of the time, what will you do? You will throw the ball in a random direction because you're not interested to basically make the ball go behind you. You threw the ball in a random direction. Therefore, what happened? Instead of 10 balls going behind past you, only 7 balls are going past you. 3 balls you caught and you basically threw them in a random direction like this. Okay, so only 7 out of the 10 balls were actually able to cross you. Okay, so basically, if I take a spectrum like this, first ball went through the boundary, second ball went through the boundary, third ball went through the boundary, fourth ball you caught, fifth ball you caught, sixth ball went to the boundary, seventh ball went to the boundary, eighth ball you caught, ninth ball went through the boundary, 10th ball went through the boundary. Okay, so basically, the 4, the 5, and the 7, okay, they are missing. These fourth ball, fifth ball, and the seventh ball are missing from the boundary. Okay, so that is a spectrum. That is an absorption spectrum. Understood? Are you able to analyze this?
Yes.
Okay,
So those will be at most.
exactly. The 4, the 5, and the 7 balls will be the missing wavelengths in that spectrum. Now it is clear, right? Now,
Yes.
basically, you could have taken that ball number 4 and threw it beyond the boundary. But it is up to you. It is up to you. You are one. You are one single person. Okay. Now imagine this, that there are 10 different clones of you in front of you, and there are 100 such balls coming like this. Okay. So you are selectively every single Akshay. Okay, you have 10 clones. There are 10 Akshas in front of you. Since all of them are identical, you are going to catch the third, the fourth, and the seventh ball only. Okay, some of the third, the fourth, and the seventh ball will actually go behind you. You will actually try to throw it behind the boundary. But it is not necessary that all the 10 Akshas do the same thing. Read. So basically, if 100 balls are coming like this, there will be 30 balls missing. Okay, 10 balls of ball number 3, 10 balls of ball number 4, 10 balls of ball number 7. Okay, so basically you're getting a band now, a complete band where out of 100 balls, 30 were intercepted, so they were missing. Here, is this picture better for you in your head? Okay, let's move on. Now, the black lines that appear in the spectrum contrast with the high intensity of non-absorbed photons. Okay, because you are not interested in the 1, the 2, the 1, 2, 3, 6, 8, 9, 10. Those were bright. Okay, these photons were bright. Only the 4, the 5, and the 7 were always missing. Those missing balls will show up in the scanner. Okay, similarly here, because these bands were intercepted, you will have a dark patch between colorful backgrounds. Okay, so an absorption spectrum can be defined as a colorful background in which a few dark lines appear. A colorful background in which a couple of dark lines appear, that is known as the absorption spectrum. Is this clear? Okay. Now, evidence, a history of spectra. Observation of atomic spectra began well before the 19th century. A knowledge of optics had existed since Roman times without any break in the Middle Eastern countries. However, it was rediscovered in the Western Europe around the 16th century. This allowed Europeans of the time to study the light emitted from hot or glowing objects. Scientists used an optical device, usually a glass prism, for those early experiments to spread the white light coming from the sun, the shortest wavelength to the longest wavelength. So, the phenomenon called dispersion of light, that is, splitting a combo of light into its independent individual spectra, okay, independent wavelength, okay, that is known as dispersion. So the early scientists used this prism to basically separate out the lights that were coming from the sun, the same order as in the rainbow. Even today, spectra are present in this linear way. Spectra in this topic are also displayed when line colored correctly and with the colors arranged by wavelength in their correct place. So we still use the concept of spectrum. Still do that. Violet, indigo, blue, green, yellow, orange, and red. Okay, that is not going to change anytime soon. Okay, it's a standard now. Now, the absorption spectra for sodium can be demonstrated with some apparatus. As for emission, a white light source emits light which is incident on a diffraction grating on the turntable of a spectrometer. So this is a spectrometer. Now, where is the white light? This is the source of white light. It could be a bulb. It could be a very hot glowing object. Okay, it is a source of white light. It could be a tungsten. It could be LED. It could be the sun. Okay. Now, what is happening? A source of white light is there. Now, a continuous spectrum, a continuous spectrum can be seen through the telescope or display on a computer monitor using sensors and softwares. When a flame is used to heat a vertical wire that has been dipped in sodium chloride, the light from the continuous spectrum is allowed to go through the sodium ions. Now, this is a Bunsen burner. On top of this, you have what? You have basically dipped a rod, okay, in sodium chloride solution. So the sodium chloride salt crystals are now stuck to the surface of that rod, okay. Now, and you are going to heat that rod in the Bunsen burner, okay. Now what has happened? Let's see. Now the sodium absorption lines seen in the yellow region of a continuous spectrum, so you are able to view some lines that are missing in the yellow spectrum, okay. The yellow region of the continuous spectrum is missing. Okay, the observation of both emission and absorption spectrum is an effective way to determine the chemical composition of a material. Chemists can quickly identify an anonymous white crystal. All they have to do is place it in a spectroscope and then it will analyze what are the various atoms that are present in creating this crystal. By placing the crystal on an inert wire such as platinum and then putting that crystal and wire in a flame, the colors of the flame give good indication of the elements in the crystal. For example, brick red means cadmium. Green means the presence of copper ions. Okay, red color, brick red color, the color that is present on all the bricks that we have. Okay, is basically cadmium. Green color means copper. A more detailed analysis of lines in the spectrum also gives a definitive answer to the question of composition of materials. Figure 14 shows the three sets of spectra. You can see that the lines are at completely different wavelengths and in completely different arrangements. All the lines are at completely different wavelengths and having completely different arrangements. Next, measurements electron volt. The photon energies and atomic energy levels difference are often given in units of electron volt. Now, what is 1 electron volt? You may think that 1 electron volt is a unit of voltage, but you may be wrong because 1 electron volt is a unit of energy. Energy, it is a unit of energy. Okay, so 1 electron volt is a unit of energy. 1 electron volt is equal to 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. If you have an electron whose charge is 1.6 into 10 to the power minus 19 coulombs and you accelerate it through a potential difference of 1 volt, energy is equal to charge into potential. So you will get 1.6 into 10 raised to power minus 19 joules. If one electron is accelerated through a potential difference of 1 volt, you get 1 electron volt. Understood? So this is a common unit. This is a common unit in atomic physics, along with the multiple kilo electron volt and mega electron volt. Kilo electron volt will be 1000 electron volts. Mega will be 10 to the power 6 electron volts. It avoids having to use large negative powers of 10. You can find a definition of electron volt in page 519. I just gave you the definition. Okay. Now, in IB physics data booklet containing a conversion unit for the product of Planck's constant and the speed of light in vacuum, Hc, you get 1.99 into 10 raised to power minus 25 joules per meter, or 1.24 into 10 raised to power minus 6 electron volts. You can use this to make the conversion from a change in the energy levels of an atom to the wavelength of photon emitted or absorbed during this change. So basically, the Planck's constant always gives us a value in joules. Okay, it always gives us a value in joules. Now, you can convert joules to electron volt by dividing it with 1.6 into 10 raised to the power minus 19. If you want to convert 1 electron volt into joules, all you have to do is multiply it by 1.6 into 10 raised to the power minus 19. Clear? Next. The change in energies delta E is equal to HF, where F is the frequency of the photon. This leads to delta E is equal to HF is equal to Hc upon lambda. Therefore, delta E is equal to Hc upon lambda. Understood? Basically, the what is the energy of the photon that was absorbed? It will be equal to Hc upon lambda. This would indirectly give you how much energy was needed for the electron to go from one energy level to the next. No, I'll repeat it again. So we know that an electron has to absorb some amount of energy to go into the excited state. Clear? It has to absorb some amount of energy to go into the excited state. So where is this energy coming from? It's coming from a radiation. Okay, in the it is coming from a radiation. Now, in that, when the radiation is falling on to this element, it gets excited, due to which what do you conclude from this? It absorbed some amount of radiation. Okay, now this radiation, when it was absorbed, you need to know what the energy level is. Okay, so you look at the spectroscope and you see, oh, 520 this thing 520 nanometers of this radiation was absorbed. You got the wavelength. Okay, so you know that delta E, the energy that was required to move from the lower to the higher energy level, that is delta E is equal to Hc by lambda. What is lambda? Lambda is the missing wavelength. Okay, it is the missing wavelength.
Yes, yes.
Exactly. You know the value of C, you know the value of H, you know the value of lambda, so you can calculate delta E. Clear? Okay, next. Now, when you know the difference between the two energy levels in an atom, you can use the delta E expression to rearrange as lambda is equal to Hc. Now, if you know the energy that was required to excite the electron, you can just rearrange the formula to get what? To get your wavelength, right? Wavelength will become equal to lambda is equal to Hc upon delta E. Just rearrange the formula and you got the new formula. For example, when an atom undergoes a transition between energy levels that differ by 1.88 electron volts, the wavelength of emitted photon is lambda is equal to what? So first things first, Akshay, look at this. We know that E is equal to HF is equal to Hc by lambda. Okay, Hc by lambda. Now, energy, this energy is in joules. Okay, This energy is in joules. Now, if I know the value of H, right? I know the value of C. So can I do energy is equal to Hc upon your E lambda? This will be energy in electron volts.
Yeah.
Okay, so H is equal to what? 6.6 into 10 to the power minus 34 into 3 into 10 to the power 8 upon 1.6 into 10 to the power minus 19 lambda. So when you do all of that, you get what? This value. Okay, you all try doing this. Okay, so what do we get? Minus 34 plus 8 is what? Minus 26. So 10 to the power minus 26 at the top upon 10 to the power minus 19. When it goes up, 1926 becomes 7, right? Yeah. So you get at the top some number called 10 to the power of 7. And 6.6 into 3 is what? 6 threes are minus 7. Yeah, sorry. Minus 7. Yeah. So 3 6 are 18. 1 3 6 are 18. 19.8 into 10 to the power minus 7 upon 1.6. Okay. So 198 upon 16 into 10 to the power minus 7. So let's divide this 198, 16, 1s are 16, 38, 16 2s are 32. This will give you 6.0, 16 5s are 16 4s, 16 3, that is 48, 49, 50. So 12.3, let's just imagine it's 12.3. So 12.3 into 10 to the power minus 7 upon lambda, or simply 1.23 into 10 to the power of minus 6 upon lambda. This energy will be in what? Electron volts. Okay, so you can remember this. This is the same thing that they have given here, 1.24. They have basically rounded it off. I got 1.23 something something, so they rounded it off to 1.24. Okay, so this is the energy in electron volts. Okay, you should remember this number so that your calculations become faster. Clear? So if you want your formula to be correct in joules, so you will write 6.6 into 10 to the power minus 34 into 3 into 10 to the power of 8 upon lambda. This will be 19.6 into 10 to the power minus 26 upon lambda joules. So one is in joules and one is in electron volts. Here, any doubts in this? You can write this down in your book if you want. So the next topic. How can emission spectra allow the properties of stars to be deduced? How can emission spectra be used to calculate the distance and velocities of celestial objects? Now, our present knowledge of the properties of stars would not be possible. It would not be possible without observation of stellar spectra. They reveal the size and the nature of stars themselves. The peak of a continuous spectra equivalent to that formed from a black body to a good approximation. What is a black body?
That's what it is all time. It is
It can absorb all types of light or it can emit all types of light when it is heated. Okay, when it is heated, it will release light. When it is absorbed, it will absorb light. Okay, given the temperature of the star. This together with the luminosity of the star, which can be deduced from its apparent brightness and distance, leads to an estimation of the radius of the star. Okay, so we can actually calculate the radius of the star by deducing the intensity of light that is coming from it. Okay, redshift is in the spectra leads to the speeds of stars and galaxies relative to us. Topic C5, and also rely on precise movement of spectral wavelengths. The fractional shift in the wavelength is proportional to the relative velocity of galaxies along the line joining the Earth. We will actually go through all of this once more, okay, Akshay, before your final exam next year, right? Next year you have the final exam, right? Before that, we will revise all the chapters once more. Okay, don't worry. Outline with reference to atomic energy levels how a discrete emission spectrum of gas is formed. Okay, now gaseous atoms in an excited state move to a lower energy state, right? Gases usually have a lower energy state. Now, the gas atoms in the excited state move to a lower energy state because energy levels of the atoms are discrete. So, discrete means what? You can only have certain transitions. Yeah, continuous energy level and discrete energy levels. How would you distinguish between them?
And discrete energy levels means like exact rate and that does not change and that
That transition.
it does not change, but
Oh,
that continuous like
you could have any values. You could have any values in a continuous energy band. You would have any values. So it basically means that electron could be anywhere around the nucleus. Okay, if it were a continuous band level, you would say that the electron is free to stay at any position it wants. But we say that no, that's not possible. Electron can only stay at discrete energy levels. Okay. Photons emitted by the gas can only have discrete energy levels equal to the difference between the atomic energy levels. The photon wavelength lambda is related to the energy by the formula lambda is equal to hc upon a. We know this. Hence, the wavelength in the emission spectra are also discrete. Okay, the emission spectrum. Now, they have given us the question. The emission spectrum of hydrogen contains an infrared line at 1282 nanometers. Calculate in electron volts the energy of a photon of wavelength 1282 nanometers. The formula is right here. Okay, 1.23 into 10 to the power minus 6 upon lambda. Okay, so you have 1.24, let's use their value itself, into 10 to the power of minus 6 upon lambda is what? 1282. 1282 into 10 to the power of minus 9 electron volts. So I can write this as 1.24 into 10 to the power of minus 6 upon 1.282 into 10 to the power of minus 12. So can I roughly cut them off?
yeah,
So I'll get 1 into 10 to the power minus 6 plus 12 is 6. So you will get approximately equal to 10 to the power of 6 electron volts. That's exactly what you're getting here. No, wait, what?
so
No, I'm such an idiot. I'm such an idiot. No, 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 no. This should have been 10 to the power minus 6. No, it would reduce. See, the decimal is going from here to here. So this number should actually increase. 10 to the power minus 9 should become 10 to the power minus 6. Oh, I'm such an idiot. So this also would get cancelled off. So you'll be left with how much? Only 1 electron volt, approximately 1 electron volt. 1 electron volt. Understood? Because I roughly cut them both. It would not be 1 electron volt. It would be less than that. Even if you write, see, you know it's above it's 1.24, below is 1.28. So even if you write 0.9 electron volt, she will give you marks. Your teacher will give you marks. Okay, let's move on. The diagram shows some of the energy levels of an atom. Okay, you have minus 6.3 electron volt, minus 3.9 electron volt, minus 1.2 electron volt, minus 1.5 electron volt. Calculate the longest wavelength. Okay, this is a very trick question. This is a trick question. Okay, now what is the formula for energy? Is equal to h mu, that is frequency, or h is equal to h c by lambda. Now, let me start this question by telling you what where will the maximum amount of energy be released? Okay, you have a glass in your hand. You are dropping that glass 10 centimeters above the ground. From 10 centimeters above the ground, you're dropping the glass. It produces a sound. It produces a sound. It's a very small sound. 10 centimeters above the ground, very, very dim sound. Now, you're dropping the same glass from a height of 2 stories. 2-story building, you're dropping the glass on a floor, on a concrete floor. The sound will be enormous, right? The sound will be enough to wake a few people who are sleeping. Okay, so when something falls from a very large height, it produces a large amount of energy. Am I right? So basically, if you want to have the longest the energy, the maximum energy possible, okay, if you want the just replace the sound energy with radiation. It's also a type of energy. If you want maximum radiation to come out, you need to fall from a large enough energy level, large enough height. So basically, from this height, if you drop straight down, you will get the maximum energy possible. So if you have the maximum energy possible, we know that energy is directly proportional to frequency. So the radiation's frequency would be maximum. But we also know that frequency is inversely proportional to wavelength.
So that's how I think. So,
The wavelength would be the smallest. Yeah. So so if you want to have the shortest wavelength possible,
wavelength is
yeah. So when the electron is transitioning from minus 1.5 electron volt to minus 6.3 electron volt, you will have the shortest wavelength because the energy will be maximum, the frequency will be maximum, therefore the wavelength would be minimum. If you want to have a longest wavelength, the energy should be very small. Where do you observe the energy level to be the smallest? When it is going from, yes, exactly. So when the transition is happening from this to this, you will get to see the longest wavelength because the energy would be the least, the frequency would be the least. Understood? Okay. So in a way, you can say that energy is inversely proportional to wavelength. From this itself, you can say that energy is inversely proportional to wavelength. Correct? So the longest wavelength will be from minus 1.5 to minus 2.3 electron volts. And the shortest wavelength will be from minus 1.5 to minus 6.3 electron volts. Correct? Now, we need to find the wavelength because the story is not over yet. We have to now find the wavelength, actual wavelength. So, we know the formula, that is 1.24 into 10 to the power minus 6 upon lambda is the energy. So, we know that energy is equal to 1.24 into 10 to the power minus 6 upon lambda electron volts. Therefore, lambda will become what? 1.24 into 10 to the power minus 6 upon energy. Okay, so you calculate the difference between these two. What do you get?
minus
Yeah, 0.8. Okay, so you will have 1.24 into 10 to the power of minus 6 upon 0.8, or simply 12.4 into 10 to the power of minus 5 upon 0 upon, no, minus 6 only, minus 6. What am I doing? Minus 6 upon 8. So what is the wavelength that you will observe?
taking 1.55 into the minus.
Okay, clear?
Yeah,
Can you just check the answer for me?
yeah.
I wrote it in micrometers. So 1550 into 10 to the power minus 9, or simply 1550 nanometers. Correct? Simple? Easy? Now, you do for the shortest one and let me know the answer.
258 nanometers.
So
2.58.
258 nanometer. The shortest wavelength will be 258 nanometer. 1.24 into 10 to the power minus 6 upon what are the energy difference that you got?
4.8.
4.8. So this will be for the longest wavelength. This will be for the shortest. Clear? Next question. Okay, identify the atomic transition that results in an emission of a photon of energy 4.00 electron volt by this atom. Okay, so you need to know if a photon of energy level 4 electron volt is emitted, then what transition took place? It's very easy, Akshay. Tell me. Where do you see a 4 electron volt transition? A difference in energy level of 4 electron volt. Between two, which two energy levels do you see?
Oh, minus, minus, minus.
That's it. So the transition actually took place from the third energy level, sorry, second excited state to the ground state. Okay, easy, right? Next one. The emission spectrum of sodium contains two lines of similar wavelengths, 588.995 nanometer and 589.592 nanometer. The lines are emitted in a transition from one of two narrowly separated energy levels, EA and EB. Okay, these are the two energy levels that you see here, EA and EB. Okay, now to another energy level, EC. So if an electron in the EA energy level gets dropped to EC, it releases a wavelength of 588.995. And when it is dropped from EB to this EC, you are getting 589.592. It makes sense also, right? The wavelength is increasing as the energy is decreasing. Okay, since EA is at a higher energy level than EB, so EA to EC would have a higher impact than EB to EC. Therefore, the wavelength of A to C will be will be less than lambda for B to C. Okay, what have they asked us? Calculate the energy of each of the photon emitted by the sodium atom. How will you do this, Akshay?
Let's give finalize. So let's give on.
No, why? You only need to answer that in electron volts. No, you do the same thing. 1.24 into 10 to the power minus 6 upon 588.995. This will be EA. Okay, into 10 to the power minus 9 comes out to what?
So
What is the answer?
zero.
electron volts, right? Now, if you want to convert it into joules, you can all you have to do is 2.105 into 1.6 into 10 to the power minus 19. This will be the answer in joules. Okay. What about EB? Again, 1.24 into 10 to the power minus 6 upon 589.592 into 10 to the power minus 9. What do you get?
Zero three.
2.103 electron volts. Correct?
Yes.
Now, calculate the energy difference between energy levels EA and EB. So, EA minus EB is equal to how much? 2.105 minus 2.103 electron volts will be 0.002 electron volts. Is the answer correct?
Yeah. So that is 2.105. Use 2.5.
Yeah, is equal to 2 into 10 to the power minus 3 electron volts. Correct?
Yes.
Okay. So, the next topic, taking Rutherford's model further, right? This is all AHL, right?
Yeah. I think there's
Bohr's model. You should actually learn this. This is actually good for you. AHL. So till here, this is also AHL.
the next thing.
Quantum physics entirely AHL.
Yeah.
Okay. I think this chapter is over, right? Okay. Anyway, if we are free, I can actually teach you this, like if you want, or simply it's fine. Okay. So, students, our SL topics are over. Okay, and the only topics that are left are AL. So, if you want me to teach you AHL also, please do like, share, and subscribe, and just comment down below. Okay, I will create the videos for AHL also in the near future. Okay, right now my priorities are to finish the SL topics. Okay, so if you like my videos, do like, share, and subscribe, and I'll meet you in the next class. Thank you so much, and have a nice day.